Now we're in Physical Chemistry, Chapter 17, Section 12. We're going to talk about trimolecular reactions, or termolecular reactions. So, let's say we have an iodine-free radical and another iodine-free radical, plus M, which we said is a third body, going to I2 plus M and giving off energy. And this is going to be in the gas phase, of course. So like I said, M is a third body. In this case, it exists to absorb the energy given off by the I, and the I come in together to make I2. So we're going to say M is a chaperone. So the energy of activation is less than 0. It's exothermic. It's going to give off energy. So, well, bad example. So anyway, if the energy of the collision would be enough to break up the I2 bond, the energy of the collision would have to be enough to break up the I2 bond. So in other words, when the I and the I come together, it's going to make I2 in a high energy state. That'd be enough for the I2 to fall back apart. So for the I2 to stay together, it has to give off energy, which gets transferred to the third body. So like I said, in this case, it's an exothermic reaction. So we need to absorb that energy somehow. So the reverse reaction is going to be bimolecular, because we have an I2 molecule, that's one molecule, and then the M, the chaperone. So we have another example, CH3 plus CH3 going to CH3. That doesn't need a chaperone because the CH3, it has 18 vibrational modes, so it can disperse all that energy from the collision. So free radical collisions, they're usually pretty low in energy. Like the energy of activation is less than or equal to 0, but greater than or equal to minus 17 kilojoules per mole. So it's not really a lot of energy. So if the energy of activation is equal to 0, then the derivative of the natural log of K with respect to T is equal to 0. Remember, capital T is temperature, and the K, of course, would be the equilibrium constant. So you get the derivative of the natural log of K with respect to temperature. It's going to be equal to the energy of activation divided by RT squared. So as temperature increases, K is going to go down for a free radical reaction. The derivative of the natural log of K with respect to T being less than 0, that also means that the energy of activation is less than 0. So with higher temperatures, the free radicals, they have so much energy that the reaction can't go forward. So as temperature increases, K decreases. And K is equal to A times E to the EA over RT. So the conclusion, if we get I2 going to I plus I, free radicals, that requires M. So it's going to be I2 plus M going to I plus M. So the rate is going to be equal to K times the concentration of the I2 times the concentration of the M. So here we go, energy versus, this is just a reaction coordinate, right? So here we have the M plus I2, here's the M plus I. So higher energy will be up here, lower energy is down here. But here's energy C2H6, ethane, or CH3 plus CH3 broken apart, two free radicals. So we broke the carbon-carbon bond. So here it goes down because we formed this bond, but there's actually repulsion between the two bonds.